All right, cool. Thank you, everybody. Hopefully people are still awake after lunch. But this tutorial slot is going to be all about temporal reasoning. So today's tutorial is going to be split sort of into two parts, roughly before and after the coffee break. In the first part, the real hope is to build sort of a strong baseline, sort of explain sort of what are the building blocks of temporal networks and temporal network reasoning that people sort of consider in general. And then in the second half, we'll sort of go in a little bit more depth. We'll talk about things that are a little bit more on the bleeding edge in terms of how people think about temporal reasoning and temporal modeling. But so that's just sort of structurally how today, or how this session is going to pan out. But I think more broadly, it's sort of useful to contextualize sort of what are the goals of this tutorial? What are we trying to sort of communicate, convey to you guys? And the goal is to give you enough of a background in temporal reasoning such that if you belong to the planning community and you know nothing about temporal reasoning, at the end of this tutorial, you should at the very least know where to go, what to look for in order to upgrade your planning system, in order to make sure that you can consider the impact of time and understand how to reason about time in conjunction with, sort of the other cutting edge research that you guys are doing. And so along the way, I'll try and sort of introduce sort of building blocks and steps to sort of explain what are the things that you should be paying attention to, how can you sort of use these in conjunction with other systems, and I'll try to interleave that with sort of the newest, latest, and greatest advances. So without further ado, we'll get started. And just sort of another thing, I really don't want this to be 3 hours of me lecturing, so please interrupt, raise your hand, do whatever, just to make this as much of a dialogue as possible. I'm sure there are things in here that are going to be a little obtuse, poorly explained, and so the more that we can sort of engage in a dialogue like this, I think the better it'll be for everyone involved. All right, so let's do it. So first, the question that you should ask is, why do we care about temporal reasoning? The first slide was temporal reasoning. I should be able to tell you why we care. And this is sort of an important point. And I think a lot of times when you think about planning in a context where you have time, where you care about time, the number one question that you should have in your head is like, how much do I have to think about time? Because one answer that works quite often is to basically say, I'm going to do every action as fast as I humanly can. And I hope that once I do everything as fast as I can, maybe some things will have to wait for other things, but eventually I will sort of achieve all preconditions that I need for further actions to take place. And if you happen to be operating a domain where you can sort of operate under that paradigm, that's fantastic. And you don't really have to think about temporal reasoning too hard in order to make sure your system works properly and you sort of achieve all the end goals that you want. But the reality of the situation is that there are a lot of very rich scenarios, very rich planning examples that we're familiar with in sort of everyday life that sort of buck that assumption. That if we tried to sort of just say do everything as fast as possible, we'd either end up with a suboptimal plan or one that doesn't actually achieve what it is that we want at the end of the day. And so one sort of really easy place to start with is to think about sort of the delivery problem. So this is, there's sort of the classic canonical, delivery truck problem in the planning world is I have a truck, it can move to different cities, it can pick up packages, it can drop off packages, and I need to make sure that each package arrives at the correct destination at the end of the day. And sort of one thing that you might reason about doing, and you might say just like, okay, I'm just going to try to move as fast as possible, and I'm just going to try to get all of my packages on the truck and then move immediately to each delivery location and drop off that package. And that approach will work, but oftentimes the types of scenarios that we have don't lend themselves so easily to that kind of a problem. So for example, in this example that we have right here, each customer has a particular delivery window. They're only home for a certain amount of time, or they only, the loading dock is only available for this truck to sort of come in and drop off the packages in these particular windows. And given these constraints now, instead of just saying, it is fastest for me to go A, B, C, D, E, you now have to think and reason and say, okay, in order for me to sort of hit these windows at the appropriate times, I have to be a little bit smarter about how I order these things. And not only that, it may be the case that, ordering might not be an issue, but another thing is, your driver sort of checks in at 6 a.m. and the first delivery spot is only an hour drive away. If this driver just sort of tried to do everything immediately as soon as he or she could, they'd be sort of stuck idling at one of these destinations at the earliest possible time. And so maybe instead you want to have that driver do something different, check in late, or maybe take some inventory back at sort of headquarters. There's sort of a lot of things that sort of come into play when we start thinking about time and when we start thinking about coordination with respect to time. And so in situations like these, we can't just say do everything as fast as possible because we're going to end up with plans that we don't like. So another sort of wrinkle when we start to think about time is the fact that we can't always control time. We can't always control the true durations of our actions. So if we think about sort of this delivery truck example, the amount of time it takes to sort of go down the highway from San Francisco to Berkeley depends pretty heavily on the time of day and the amount of traffic. So on a good day, it might take 30 minutes. On a bad day, it might take 2.5 hours. And from a planning perspective, that difference sort of has a pretty large impact on sort of the end result of our plan and sort of the actions that we choose to take. And so what we need to be able to do is when we think about time in this context, we have to make sure that we can consider time that is uncertain. We have to consider events whose timing is outside of our control. So the third thing that I kind of want to talk about, and that we'll get to a little bit more sort of in the second half after the coffee break, is multi-agent coordination. So when you're dealing with multiple agents who are trying to sort of operate with each other, or if you think about sort of how we as humans sort of do multi-agent coordination in a nominal sense, we use time as sort of our coordination mechanism. We say, hey, the tutorial is going to start at 2 p.m., so everyone is going to show up here and make sure that they finish their lunch by 2 p.m. And in a world with multi-agent coordination under timing constraints, it's important to sort of understand what are the, sort of each agent has sort of its own sets of constraints, and there may be limitations in terms of how tightly coupled different agents can be. So for example, if I'm going off and I'm having a meeting, I'm out of communication during the times of that meeting. And so one thing that we're going to talk about a little bit later is how temporal reasoning is sort of critical and very inherent to the problem of multi-agent coordination. And if you want to sort of consider planning in a multi-agent context, understanding how you can use time and how you can leverage time to make these commitments, break these commitments, is something that's going to be very useful for us going forward. So broadly, those are the reasons why temporal reasoning is important. It's something that we care about. And when we think about temporal reasoning in planning, it's useful to try and sort of think about, I have a planning subsystem. I want to start thinking about time. What are the ways in which I can sort of add temporal reasoning to that system? And there are really two ways. The first way is you have your planning subsystem and it generates candidates for you, and you evaluate those candidates for consistency. And so this approach is nice because it's very easy to integrate and it's very easy to build because you don't have to mess with your existing planning subsystem. All you have to do is evaluate candidates, and just if, for whatever reason, that candidate is temporally inconsistent, you ask your planning subsystem for yet another candidate. So the advantage of sort of this first approach is it's very easy to implement. And so you can use something off the shelf in order to give your planners this temporal capability. But sort of on the flip side, the second approach is, what advantages can we gain if we integrate temporal reasoning more in a deeper way with our existing planning subsystems? So for example, your planning subsystem might be exploring one area of the search space, and this entire area of the search space has sort of a very simple temporal inconsistency. And what you would ideally like to do is sort of incrementally check temporal consistency as you go, and sort of and giving you sort of the ability to prune bad branches ahead of time, and move to the areas of the search space that are actually going to be the best for you going forward. And so today, as we sort of go over these different temporal reasoning approaches, these different temporal models, one thing that I will try to pay very close attention to is sort of giving you each of these two mechanisms. So one, there should be a mechanism that explains how you can just check for consistency off the bat with a fully formed plan. And then second, something that is useful is thinking about how you can check temporal consistency incrementally as you go along, reusing some of the computation that you've already done. Yes?
So does that mean it's built into the planner itself, or is it something you have to add on to an existing planner?
So a lot of it depends on sort of the planning subsystem itself, but the algorithms and things that I will discuss will be things that you can more or less keep a little bit separate. And you can, in theory, run these two subsystems in parallel, but the idea is you add you would sort of try to fold it in a little bit more directly. So as you generate sort of a partial candidate, you would evaluate that partial candidate for temporal consistency, and you would use sort of information about temporal consistency of previous partial candidates that it was derived from. Does that make sense? Did that answer your question? Yeah.
Yeah, I guess I would even say it's stronger, right? Which is, I do think the technology is there where you can view it more as a black box, right? And then if you have a good planning algorithm which can generate a sequence of actions, right, then you can call these a subroutine. Right? It is the case that you have to deal with the interleaving between them, right? But you don't have to go into the details of the algorithm.
Yeah, that makes sense.
Yeah. Great. Any other questions before we continue? Great. Also, just as a heads up, I have this bad habit of speeding up the longer that I give a presentation, and so if you ask a question, it will slow me down. So, yeah. Just as a heads up as we continue onwards. So again, I wanted to sort of lay out very concretely the goals for today is to give you just sort of a from first principles approach to thinking about temporal reasoning in the context of your existing planning subsystems. I want to make it easy for you to add temporal reasoning to the work that you guys are already doing. And then along the way that we're going to do so is by introducing you to a lot of different types of temporal models. We're going to go over sort of what makes them good, what are their existing limitations, how do we represent them, and then importantly, how do we actually check these things for consistency overall, and then, of course, how do we handle these incremental changes in order to give us these two flavors for types of algorithms that you can use to build up your system. Alrighty. So without further ado, let's jump right in. So the first thing that we want to do is we want to model a temporal schedule. And when you think about modeling a temporal schedule, one thing that's sort of, we are broadly in the AI community, and so what we want to do is we want to think about modeling time, modeling, temporal reasoning in the context of planning, much in the way that we talk about time in natural language. And here, it's useful to sort of turn to Allen's interval algebra. And with Allen's interval algebra, we have just sort of a very small set of relations between pairs of actions or pairs of events that each have durations associated with them. And the nice thing about this is there's a very limited set of ways in which two actions can be related to one another. And so the intuition that we want to have here is that any formalism that we introduce or that we use that talks about time, that talks about scheduling in some broad context, should be able to capture, it is good if it captures sort of everything that is described in Allen's interval algebra. And the place that we start is with simple temporal networks. So simple temporal networks are sort of the base temporal structure. And if you look at all into the temporal reasoning, temporal modeling community, most networks are sort of derived in some sense from the simple temporal network. So STNs are relatively straightforward. They consist of a series of events. So in our case, our events are denoted by uppercase letters A, B, C, D. And the only types of constraints that we permit in a simple temporal network are pairwise binary constraints that constrain the difference between two events. So in other words, over on the right, B minus A is between 25 and 40, basically says event B must happen between 25 and 40 minutes after event A. And it turns out that this construction is actually quite powerful, because this construction, as it's formulated, allows us to describe quite a few of the things that we talked about in Allen's interval algebra. But it actually goes sort of a step further, because an important thing when we think about how we think about time and how we talk about time is we also sort of have sort of nominal use of constants. So we say things like, let's meet up for the tutorial at 2 p.m. This tutorial will take at least 90 minutes. 30 minutes after the first session ends, the second session begins. And so we want to be able to take advantage of and use sort of constants in the same way. And the simple temporal network allows us to sort of lay them out as such. And so given a simple temporal network formalism, the big question or sort of the goal of when you're given one of these things is to find an assignment of values to all of the variables such that all of the constraints are respected. So in other words, we need to pick actual physical times for A, B, C, D such that all of our constraints, all the differences between pairs of events fall within the desired ranges. And sort of one really nice thing about this approach is that we can actually take all of the constraints that we had previously and turn them into a set of linear inequalities. So when we had B minus A must be between 25 and 40, we can sort of rewrite that in our heads as 25 is less than or equal to B minus A is less than or equal to 40. So that gives us B minus A is less than or equal to 40. And then if we flip it around, we get A minus B is less than or equal to negative 25. And when we sort of write all of these things down as a set of linear inequalities, we can just plug it into an LP solver and it'll give us an answer. And we can even add objectives on top of it. So we can say, I want to minimize the amount of time between the start of event A and the end of event B, something like that. And already, if you guys just sort of left at this point, you would be ready to go and you could add temporal reasoning to your existing planning subsystems, because all you have to do is you take some plan that you've derived. It has some sort of relationships between when events start and when events end. You throw it into an LP solver, anything off the shelf, and it'll spit out a solution. And it'll tell you either, yes, it is possible for us to construct a schedule. In fact, here it is. Or it'll say, no, it's impossible for us to construct a schedule. So we've already sort of hit that first bullet in terms of we want just sort of an off-the-shelf algorithm that we can use to evaluate candidates that our planning subsystem has fully generated for us. But again, the question that we ask at the end of the day is, we want to do incremental planning. And there's probably something, you could certainly call the LP for every partial candidate that you've generated, the LP solver for every partial candidate. You might be able to, if you know a lot more about LPs than I do, maybe you can do something really tricky in terms of iteratively adding constraints and using previous solutions as incumbents. But that's a little complicated for me. And so the big question that I want to ask is, can we do better? And the answer is yes. Or at least in my opinion, the answer is yes.
It's probably also worth saying that a lot of early temporal planners just would reformulate it as an LP, right? But that's not, as hopefully you'll see here, is not a very efficient approach.
Yeah. So sort of the big jump and the big leap in reasoning about temporal networks comes in this reformulation. So one really nice thing about simple temporal networks is that they can be reformulated as what we call a distance graph. So what exactly is a distance graph? Well, for every inequality that we had, you remember we rewrote everything in terms of linear inequalities, that is of the form b minus a is less than or equal to k. We basically can construct a graph where all of the edges are just all of the time points, all of those variables that we need, or excuse me, all the nodes are all of the time points, and all the edges are just derived from these inequalities. So if we have b minus a is less than or equal to k, we create a new edge from a to b with weight k. So for example, we had b minus a was less than or equal to 40 in our previous example, and so we rewrite that just here as an edge from a to b with weight 40 overall. And so this is great. You're looking at this and you're like, how does this help me figure out what is an appropriate schedule? Well, one really nice thing about this approach is that every edge in our distance graph actually maps one-to-one with one of these linear inequalities that we had written previously. And so one thing that we're actually going to be able to do is by tracing out individual paths in this graph, we can then actually construct we can derive new implicit constraints that existed on sort of the original STN, on the original system that we had. So to give a quick example, consider the path from A to C to D to B. So if we look at it just in the context of this graph, we see that the graph has the path has weight 20 overall. And one thing that we can do is we can take each of the constituent edges and rewrite them in terms of the linear inequalities that we had previously. And one sort of really nice thing that we see is that these linear inequalities have this telescoping property. So as we sort of trace out a path on our graph, the resulting inequality that we get at the end of the day basically just looks like head of the path minus tail of the path is less than or equal to weight of the path overall. So this is, yes, question?
Sorry, why the distance graph has the weight 20? Sorry, path has the weight 20.
Yes, so that's because we take A, C, D, B, and here 0 plus 50 minus 30 is 20.
Too late, too soon after lunch.
Another question, or? No. Great, yeah, so good. It is after lunch. It is good to double check my math as well. So the really nice behavior that we have here is that if we explore this distance graph and we look at paths that we see, each of these paths corresponds to a new implicit derived constraint that we can use and we can further reason about. And so we can go one step further. And so one thing that's useful for us to do is to think about what happens when we actually have a negative cycle in our graph. So for example, if we sort of completed the path that we had previously, and so we go A, C, D, B, A, we see that this is a negative cycle in our graph. It has total weight -5. And so if we think about what that means in terms of what we had just discussed previously, that means that if we take all of the edges in our cycle and we sort of line up the inequalities that they sort of came from, what we would see is that we'd get sort of a telescoping sum on the left-hand side where you would eventually end up with a minus a because that is the head and tail of this path. And so on the left-hand side, you would get 0. On the right-hand side, you get whatever the weight of this path is. And in our case, this path is our cycle, our negative cycle. So on the right-hand side, you have now -5. And so what we see is that the resulting combination of these linear inequalities tells us that 0 is less than or equal to -5. Or in other words, these 4 inequalities cannot all hold simultaneously. So this gives us a contradiction. And this actually gives us a very easy way now to check whether or not an STN is consistent. Because now all that we have to do is we turn it into one of these distance graphs. We run just sort of whatever negative cycle detection algorithm you want on it. And if it returns a negative cycle, then we know there's an inconsistency. And it's pretty easy for us to prove. So. And it turns out that this is actually a necessary and sufficient condition. So if we know for a fact there is no negative cycle in the graph, we can actually relatively straightforwardly construct a schedule as a result. So this is really nice because I don't know about you guys, but I like thinking about graphs a little bit more than I like thinking about big hairy LPs and how to incrementally adjust my LP. Whereas if I wanted to think about sort of incrementally adding a new constraint, adding a new event, we have tons of algorithms for how do you actually incrementally adjust a graph. How do you incrementally check or check things like all pair shortest paths, consistency, et cetera, et cetera. And sort of another sort of very useful tidbit, and one that sort of requires a little bit of work on pen and paper, is that if you take sort of the original LP formulation that we had, and you look at the dual of that LP formulation, the dual problem is actually exactly the problem of finding a negative cycle in this distance graph. So we're not doing anything totally clever, or I guess maybe we are doing something clever here, but it's not something that's completely far-flung from sort of the original problem itself. It's sort of in this problem's nature that finding a negative cycle has something very, very, it is very, very similar to sort of constructing a valid schedule.
So what about the cost of turning the original LP into this graph?
Yep.
What does that look like?
Yeah. So the cost of actually performing this transformation is quite small. So it's more or less linear in the size of the original problem because if you had n time points or n variables in the LP, you write each variable as just a single node in your graph, and then for every actual inequality that you had in your LP, every inequality corresponds to exactly one edge. And so as a result, writing down this graph is proportional in time to the amount of time it takes to write down your LP.
And you do that by inch?
The transformation?
Yeah, transformation.
I mean, you could, if you have a computer or an algorithm, it'll do it for you. But yeah, you sort of write those mappings one-to-one, and and then all you have to do is plug this into any old off-the-shelf algorithm for finding a negative cycle. And so there are sort of a few options available at your disposal. These algorithms are like sort of tried and true. They have Wikipedia pages. So Johnson's algorithm will give you all pair shortest paths and also let you know if there's sort of a negative cycle along the way. If you just care for consistency and you don't care to actually extract the schedule, then you can use Bellman-Ford. Bellman-Ford runs in O of mn time, and these graphs they actually tend to be quite sparse. So the number of edges in the graph is actually tends to be quite low. So Bellman-Ford ends up being very, very efficient for solving this problem. And of course, if you wanted to sort of think about incremental algorithms for actually solving it, if you have sort of an all pair shortest paths representation, and you want to add a new edge, and you want to ask, does the insertion of this new edge create a negative cycle? The trivial algorithm where you would just sort of do a double for loop works in O of n squared time and does sort of exactly what you'd want. But of course, there's sort of a very, very large wealth of research in terms of other algorithms that you can use. But the big takeaway from sort of this section, we're like 25 minutes into the talk. If you left right now, you would be well on your way to being sort of a temporal reasoning expert, because we know how to model these temporal planning problems. We basically say, okay, we take sort of a candidate plan or a partial plan, and all we have to do is specify what are the events that we care about and what are sort of the relationships that we care about. And we know how to basically convert anything that we can say in English language more or less into this simple temporal network formalism. Second, we know how to sort of check candidate plans for temporal consistency. So the easy way for us to do this is either one, just throw it into an LP solver and call it a day, or two, sort of convert it into a distance graph and check for a negative cycle. And then three, we have, we know how to sort of maintain a data structure that makes incrementally checking consistency relatively straightforward. And in our case, this data structure is going to be this distance graph. We maintain this distance graph for every partial candidate that we generate. And as long as each candidate is consistent, we can sort of use that information as we go forward to consider future candidates. Questions on this part? Simple temporal networks? You guys are all experts. You guys know it? All right, great. So let's turn it up a notch. Let's think about temporal uncertainty now. So STNs are great, and they give you a ton of power, and they make it really easy to start thinking about time. But one of the big drawbacks to using STNs is they assume that all events are within your control. So if we think back to the morning commute example, or I'm trying to drive from San Francisco to Berkeley, it could take anywhere between 30 minutes, or it could take anywhere between 20 minutes and 2.5 hours. Highly variable depending on traffic. If you sort of took that constraint and you gave it to your STN and you said, hey, go solve this STN, your STN solver would say something like, oh, great, why don't you just have your commute today take 20 minutes, and then we can sort of get everything else done. And as we know, that's kind of ridiculous and sort of leads to, you can't actually just sort of define a priori, this is how long my commute is going to take. We have to be able to reason about events that are outside of our control, or events that have sort of variable outcomes depending on sort of other external states of the world. And so because STNs aren't quite equipped to handle this, we have to now consider a different model. And so the new model that we're considering is, appropriately enough, called Simple Temporal Networks with Uncertainty, or STNUs for short. And so STNUs now give us a way to directly model bounded uncertainty between events. So if I can give you those a priori bounds, and I can tell you there is no way that my commute takes less than 20 minutes, and no way that my commute takes more than 2.5 hours, then an STNU is perfect for you, because it allows us to model it faithfully and actually come up with sort of solutions. And I'll get into what a solution means a little bit more later. But something that is going to be just a little bit useful is pictorially how we sort of describe these things. So again, just like in STNs, we have these nodes A, B, C, D. And these nodes are going to represent the individual events. In this case, only some subset of these events are ones that are schedulable by us. And we have two types of edges. And so these edges, as they're drawn here, either represent what we call requirement edges, links, constraints. Edges, links, constraints I might use interchangeably, so raise your hand if you're confused by what I'm saying at any point. Requirement links. And this here is a contingent link or an uncontrollable link. So whenever you see this dashed arrow right here, that means that we have one of these commute type relations where, or I shouldn't use the word commute, one of these like traffic type relations where there's some bound that I know of on sort of the duration of this activity, but I don't know exactly how long it will take until runtime. Yeah?
Is it possible for that lower bound to be negative? Or in other words, are you certain about the direction of the link?
Yeah, so in general, we make the assumption that the lower bound cannot be negative on that. And so the intuition here is that for each one of these uncertain events, we're going to assume that there's some event that starts or triggers the action, and then some amount of time that is not determined by us will pass before it actually finishes. So in the driving example, when I leave home, that's sort of the start of the action, and so there's no way I arrive before I start. It is a good question, though, because one thing that you might want to ask about is like external events that don't have one of these explicit triggers. Like if I wanted to model when it starts raining, then I would just have some anchor point in my plan that says I am only considering things that happen after 4 a.m. or something like that.
I'm just trying to understand what's the equivalent of the negative link.
In
from the previous diagram in this one.
Wouldn't that be like reversing the direction of the arrow if you make it negative?
yes. So if we're not worrying about this, and we're sort of thinking about what do negative numbers mean here, then yes, negative numbers would be like replacing the direction of the arrow. Let's see. So for example, if this is not a good example, but if I had B going to D, and it could take anywhere between 5 and 10 minutes. So this is saying that event D must happen between 5 and 10 minutes after event D. We can rewrite. This is sort of equivalent to, D minus B is within the range 5 to 10, which we can rewrite as 5 is less than or equal to D minus B is less than or equal to 10. Make it a negative. Negative 5 is greater than or equal to B minus D is greater than or equal to negative 10. And so this is exactly equivalent to B, D, arrow going backwards, negative 10, negative 5. So so negatives here can be sort of swapped. Negatives can be a little funky to think about because it's easiest to think about this in terms of like this number says this event happens within this range after this event, but a negative number in there means that it could happen before. This is a good question, though. Did that explanation help?
Yeah.
Somewhat, maybe, not that much.
I'll see.
Okay. Please ask more questions. So this is important. If sort of the setup here is not clear, it's worth spending the time. All right. Well, please feel free to interrupt as we go forward. But so the big thing about STNUs is now we have these sets of events that are within our control and these sets of events that are outside of our control. And we still want to maintain sort of relationships and guarantees between these things. So even though event B is outside of my control in this example, I still want to have this guarantee that event D happens 20 minutes exactly after event B. And so now it becomes a question of, so previously when we talked about STNs, the solution of an STN was a schedule where it basically said, here is when every event will happen. And now applying that exact solution model to STNUs doesn't quite make sense. One thing that we might be able to do, and in fact one thing that we can do, is we can say, well, let's see if I can construct a schedule for all of the events that are within my control. So in other words, can I construct a schedule for everything else such that no matter how this uncertainty shakes out, I have a guarantee that all of my constraints will be respected at the end of the day. And so here, I think it's useful to give just sort of a brief example. So in this example, I'm back in Cambridge, and I want to go see a movie. It's 7 p.m., and it takes me roughly between 20 and 40 minutes to drive to the movie theater, and the movie starts at 8:15, and I want to see this movie. So back in Cambridge, or Somerville rather, we have the Somerville Theater. So the Somerville Theater is great. It used to be like a real theater, like people put on plays there. It was converted into a movie theater. And the really nice thing about the Somerville Theater is that in their basement they have the Museum of Bad Art. And so with the Museum of Bad Art, the curators basically just like go around, like pick up pieces of art off the street or from Goodwill, or like actually purchase them from galleries and put them on display for you to see. And the art there is like truly horrible, but it is very entertaining to go check out. And so of course, if I'm going to see a movie and I'm driving all the way to Somerville Theater, I want to spend some time at the Museum of Bad Art. So I've decided, I need to spend at least 30 minutes at the Museum of Bad Art in order to get my fill, but I don't want to spend more than 45 minutes. If I spend more than 45 minutes at the Museum of Bad Art, I go a little crazy. So I want to spend between 30 and 45 minutes at the Museum of Bad Art. I'm leaving home at 7. It takes me roughly between 20 and 40 minutes to get there. And sort of the last question that I want to ask is, when should I be in my seat? When should I leave the Somerville Theater, when should I leave the Museum of Bad Art to get to my seat? And I certainly don't want to be late for the movie. That's sort of a no-go. So I have sort of an upper bound that I can't be in my seat later than 8:15. But I also don't want to sit in my seat and look at previews for too long. So I'm going to say I don't want to spend more than 15 minutes watching previews. So given this ginormous setup, a big question that you want to ask is, one, can you model this thing as an STNU? And two, can we come up with a solution for whatever a solution happens to mean? And so the answer is yes, we can model this as an STNU fairly clearly. There are some things that are within my control, i.e. when I go to my seat, when I leave home, but there are some things that are outside of my control, i.e. how long it takes for me to actually drive from home to the Museum of Bad Art. And so one thing that we might want to ask is, well, what if we just constructed a schedule for all the events that were within my control? So in this case, only events A and events C are within my control. I've just sort of made the assumption that event A will happen at exactly 7 p.m. So really, there's only one thing that's within my control, event C. So I have to pick a time to be physically in my seat, and I want to make sure all of these constraints are respected. So one thing that I might try is just say, like, OK, I'm just going to get to my seat at 8:15, exactly, on the dot. And so that works sometimes, but if my commute only takes 20 minutes and I decide I want to be in my seat at 8:15, I'll spend 55 minutes at the Museum of Bad Art, which is way too long. So in order to account for what might happen if my commute takes 20 minutes, I can't be in my seat any later than 8:05. So now I've decided 8:05 is when I'm going to be in my seat. Let's make sure that it works for all the possible situations. But now if my commute takes the full 40 minutes, then I only have 25 minutes at the Museum of Bad Art. And so what we see is that this approach of sort of pre-constructing a schedule ahead of time, if it works, is great. But in this situation, it clearly doesn't. And as I'm describing this to you, you guys must be in your heads be saying OK, well, sort of the very easy, rational thing is let's have a policy. If my commute takes less than 30 minutes, say, let's spend a full 45 minutes in the Museum of Bad Art. And if my commute happens to take more than 30 minutes, let's spend exactly 30 minutes in the Museum of Bad Art and then go quickly to my seats. And so in fact, this is in fact sort of a big distinction in sort of the world of STNUs. And when you're given an STNU, one question that you have to determine is what kind of controllability you're checking for. So the previous thing that I described, where you sort of pre-compute a schedule, is called strong controllability. It's because I want a schedule that is robust to any sort of uncertainty that manifests in the execution of the plan. In contrast, dynamic controllability is something that we sort of more intuitively feel like matches our assumptions of how we should actually be doing scheduling, temporal planning, incorporating time into our plans in the real world. And dynamic controllability basically says, I just want to know that it will be possible for me to sort of come up with a valid schedule in the moment, but I'm allowed to actually, in the moment, incorporate information. So after I'm done with my commute, I clearly know how long my commute took. Therefore, I can take that information and incorporate it and use it in my policy in order to figure out when should I actually arrive in my seat at the movie theater. So that's great. But one question that we really want to ask is, how hard is dynamic controllability? And actually, when people first talked about dynamic controllability, people initially thought that this was a p-space hard problem. And sort of the reason for that is, for some STNUs, you can actually think of it as almost like an alternating game. So I go first. I say, I'm scheduling when I leave work at 7 p.m. Then nature goes. Nature says, OK, great. Your commute is going to take now 28 minutes. Now go. Now try and figure out what you do. Then I pick another action. Then nature responds. And we sort of go back and forth in this way. And it turns out that while the mapping isn't quite 100% there, it turns out that you can sort of describe an STNU kind of as what's called sort of a quantified linear implication. So basically, the second half of that implication, that Cx is less than or equal to D, is basically the full set of constraints that I'm responsible for scheduling, i.e. the scheduler is responsible for scheduling. And then the Ax less than or equal to B is just some sort of, it's to clean up the notation a little bit. But it basically just says, so long as nature sort of respects its rules, so long as nature exists within those bounds that we determined ahead of time, i.e. my commute will take between 20 and 40 minutes, so long as nature picks a value in there, I need to be able to make sure that all the other constraints are respected. But in any case, so if we look at sort of that set of alternating quantifiers, this feels a lot like sort of the quantified Boolean formula problem, so which is sort of the canonical p-space hard problem. And that problem is basically, you have a series of alternating quantifiers for all exists, and then some 3-sat problem, more or less. And so given this, dynamic controllability seems like something that is very hard. But remarkably enough, we can actually solve dynamic controllability in STNUs in polynomial time. And this graph, you don't have to worry about it, but the reason it's here is basically just to explain to you is that there's a huge, huge alphabet soup of different types of temporal networks, and all with different features and different properties. But the thing that's actually quite remarkable is that for all of the ones that have sort of this notion of temporal uncertainty that we've talked about, STNUs are the only ones in which we can evaluate dynamic controllability in polynomial time. You add any sort of additional wrinkle, conditional constraints, disjunctive constraints, and then immediately this problem becomes p-space hard. So there's something quite special about STNUs that's sort of worth thinking about. But again, the purpose of today is to give you the tools and the intuitions behind how you can sort of use these things in sort of your existing planning subsystems. And so STNUs, so the thing that you should take away from this is just that STNUs are very nice because they allow you to include temporal uncertainty and still allow you to quickly determine whether or not your candidate solution is temporally consistent. And so the big question that we want to ask is, how can you actually do this? Can we sort of do things that were very similar to what we did in the STN in order to check, in our case, dynamic controllability? And so the intuition here is that we're going to try to do something very similar to what we did for STN. So remember, the thing that made STNs very nice to deal with was the fact that we could turn it into one of these distance graphs. And when we turned it into a distance graph, we just searched for a negative cycle. And these things were very easy for us to do in comparison to a lot of other approaches. And we want to do the same thing for STNUs. But again, the thing that's going to be a big wrinkle for us are these contingent links or these uncontrollable links, uncontrollable actions, because these events are going to be things that are outside of our control. And so we need to almost be able to handle both, sort of both ends of the spectrum, both when it takes as long as possible and when it takes as short as possible. And so the way that we're going to do so is we're going to create this thing called a labeled distance graph. So a labeled distance graph is very similar in spirit to a distance graph. So the way that you sort of start with constructing a labeled distance graph is you pretend your STNU is a full-on STN and you construct a distance graph. Once you do that, you're halfway done. The second thing that you have to do is you have to introduce what are these labeled edges. So I apologize if this is a little small, but we have these two new labeled edges that we've introduced in our distance graph that sort of correspond to this contingent link that we have over here on the left. And so the big question is, so first, sort of structurally, how do we construct these labeled edges? So for the lower bound of our contingent link here, we create a forward edge that has a lowercase label, and the label is always just going to be sort of the endpoint, or the event that is outside of our control. So the lowercase edge is going to be going in this forwards direction, and it's going to take on the value of the lower bound. And then the uppercase labeled edge is going to take on the reverse direction, and it's going to take on the negative of the upper bound. And so that's just structurally what they are. I haven't told you what they mean. In order to understand what they mean, it's useful for us to, again, think about what ordinary edges in our graph meant. So again, ordinary edges corresponded to linear inequalities. So that 20 edge from B to C, from B to D, basically says D minus B is less than or equal to 20. So in our case, what these labeled edges are going to represent they are going to represent inequalities in the same way, but they're going to represent conditional inequalities. Or to put it a different way, the normal unlabeled edges in our graph represent constraints, ordinary constraints. And the labeled edges in our distance graph are going to represent conditional constraints. So what are the conditions that they encode? So this lowercase b basically says that if this associated contingent link that ends at b takes on its lowest possible value, then this constraint holds, i.e. then b minus a is less than or equal to 0. And we can sort of see very naturally that if this took on its lowest possible value, then a and b both happen at the same time. And so, of course, b minus a is less than or equal to 0, and a minus b is less than or equal to 0, because b equals a. And sort of in a similar fashion, the uppercase labeled edge is again, it's another conditional constraint. And the condition here is that this constraint applies when the associated contingent link takes on its maximum possible value. So the idea here is all that our distance graph is just a set of constraints. And by tracing paths, we can sort of implicitly derive new constraints. But now that we have sort of these labeled constraints, the paths that we trace out, if they happen to include these labeled constraints, these labeled edges, they're going to be conditional constraints that we've derived. So if I take this lowercase b0 edge, and then I go from b to d with the 20 edge, then I can combine the two together sort of in the same way with those telescoping sums. And now I'm saying that there is an edge from a to d with weight 20 and label lowercase b that says if this event takes on its lowest possible value, then d minus a is less than or equal to 20. Are there questions on this? Yes?
What if you had more conditional constraints on that path?
Yes.
How would you determine the label for that whole path?
Great. Yeah. So I think the way that you should think about it is that if you had multiple labels on that path, then you would take the union of them. And so it would be like if this constraint holds and this constraint holds and this constraint holds, then we sort of evaluate the whole path. It's a good question. Any other questions? Great. Please sort of jump in. This is sort of where things certainly start to get a little hairy, a little gnarly. Yeah, so we'll continue. So of course, we have this labeled distance graph representation, and so we're tempted to basically do the same thing that we did for STNs, which is let's find a negative cycle. If we find a negative cycle, we have an inconsistency. If we don't find a negative cycle, then we're good to go. So it turns out if we don't find a negative cycle, we are good to go. But we almost trivially have a negative cycle. So here, again, this forward edge with 0 and this backward edge with negative 30 trivially forms a negative cycle. And so it turns out that any STNU that has one of these contingent or uncontrollable links, its labeled distance graph is going to trivially have a negative cycle. But if we think about sort of what a negative cycle means, or if we think about what that particular negative cycle means, that particular negative cycle actually doesn't concern us. We don't care about that negative cycle because this negative cycle, as sort of was mentioned earlier, has to take sort of the conjunction of these two conditions, i.e. condition 1, this edge holds and is enforced if this takes on its lowest possible value. The second condition the second constraint holds and is enforced if this takes on its maximum possible value. So that negative cycle that we found actually doesn't, if we tried to combine sort of the two sort of corresponding constraints together, we would get sort of nothing. Like they don't combine in a natural way because the two preconditions of the two constraints are in opposition to one another. So we have to be a little bit smarter about how we construct these paths. Yes?
You're probably going to say it anyway. Does that mean that they're exclusive when we do a check for a negative cycle?
Yes. So if you find a negative cycle and you have both the lowercase and uppercase variant of an edge, there's a little bit of additional nuance that I will get into, but yes, if you just have the uppercase and lowercase variant sort of abutting each other, then it's sort of a no-go. It doesn't sort of prove what we need it to prove. That's a good question. Was there another hand? I thought I saw another one. All right, great. But again, please jump in with questions on this because this is sort of the heart, the meat, maybe the scariest part of this. So if we want to, so if we want to sort of take the approach that we did with STNs, we have to be a little bit smarter here. So we can, of course, sort of combine edges sort of in sort of the traditional way, and we take the union of all of the paths together. And that generation strategy would work, and we could sort of like go ad nauseum trying to sort of combine all things that we can together. But one thing that's sort of useful for us to think about and to remember is that the whole thing with dynamic controllability is that we care about time itself. We care about time moving forward. In the world of simple temporal networks, we didn't really care that the variables that we were playing with actually represented time. We were just like, they are variables. We throw them in a pot, and we get an answer. But here, we're actually going to be sort of, we actually want to be sort of a little bit more methodical and a little bit more careful when we think about sort of time. And actually, as we sort of use these things and we think about time a little bit more deeply with respect to these constraints and what they mean, we're going to learn, we're going to actually generate constraints in a way that make it easier for us to reason about the system as a whole. And that may have made no sense. So what I'm going to do is I'm going to jump into a specific example. So these are some example sort of edge production rules. And I'm just going to talk about the first one very briefly. So the first one is what we call a lowercase reduction. So the way that it starts is we assume that we have some edge from A to B with lowercase label b and weight u, and some other edge from B to D with weight v. And if we ignored everything here and we just sort of looked at these two, it's totally reasonable and totally fine for us to say, okay, great. If we take these two edges together, we can combine them and create a new edge from A to D with lowercase label b and weight u plus v. And this is just because here we take these, we transform them into their corresponding linear inequalities with the associated conditional constraints. And boom, we get sort of the output that you'd expect. It's just sort of a mapping, transform, map back. The thing that I want to talk about, though, is sort of where time comes into play. And so it turns out that if we say that if v is less than 0 in this particular setup, the output edge that we get is just A to D with u plus v and no lowercase label b. So without sort of explaining why this works the way it is, this is really powerful because this says that there are certain sort of paths that we can explore in our graph that allow us to drop these labels altogether. And remember, the reason the labels were sort of tough or problematic is we had to keep track of, okay, does this label conflict with this label? And if so, then the negative cycle that we found doesn't matter. But if we have a way to sort of remove these lowercase edges as we explore our path, as we walk through our graph, then we now have a way to, then it becomes much easier for us to check whether or not we run into one of these inconsistencies. So why exactly does this rule work the way that it does? So one thing that's worth looking at is sort of to take a look at sort of like this representation of this problem in a way. So we know that D must happen at most v units of time after B. And so this is where sort of the negative numbers get a little funky and sort of mess with our heads a little bit. Because v is less than 0, that means D must always happen before B. D must happen before B. This is sort of something that we know to be the case. So if D happens before B, we need to make sure that when B happens at its earliest possible time, 1, D happens before it, and 2, D happens far enough back in time such that this upper bound of v is respected. It's a lot of letters. It doesn't make a lot of sense. They're all jumbled in my head. So let's put numbers in here, okay? So we have some variable amount of time that elapses between A and B. That is some amount of time between 10 and 30. We know that D must happen between 5 and 25 minutes before when B happens. So we know that D must always happen before B because it must happen at least 5 minutes before B. So one question that, and so what we want to do is we want to show why it must be the case that we add this edge here, or why must it be the case that D minus A is always guaranteed to be less than or equal to U plus V. So not conditionally less than U plus V, but always less than U plus V. And one thing that we can do is sort of a very silly proof by contradiction, at least in our heads, not a real proof, but imagine, so U plus V in our case, so U is 10, V is -5, U plus V is 5. So imagine that we said, it's okay, we don't have to execute D within 5 minutes of A. Let's try 6 minutes. Let's see what happens if we pick 6. So if we pick 6, we still know that we're always executing D before B. So we're sort of good on sort of box number 1. We check that off. But because we executed D before we actually saw what the value of B was, it is possible that B happens at exactly 10 minutes. And so if B happens at exactly 10 minutes, and we said, hey, this guy is going to, D happens 6 minutes after A, this guy happens 10 minutes after A, then we miss out on this window. We're actually at -4, which is outside of this window. So if you're a little confused about exactly sort of how this rule played out, don't worry. The big thing that you should sort of keep in your head and you should realize is that there are sort of a set of rules that allow us to go from these conditional cases to unconditional cases. And by being strategic about how we explore the graph, how we construct our paths to sort of derive new constraints, we can eliminate a lot of these sort of conditional constraints in favor of unconditional constraints and reason about our graph much more efficiently. And so, so if you did sort of follow all that and you totally get it, there are, other things to sort of know is that we have sort of a similar analogous instance with this cross-case reduction. And so in this cross-case reduction, it looks the exact same as the lowercase reduction, except now we have that the second edge is in fact a conditional edge, and sort of all the reasoning of the logic works out sort of in sort of a similar way. And so the big reason that I showed you these 5 rules is that these 5 rules, if we sort of apply them to our graph ad nauseum, actually are sufficient for us to determine whether or not our STNU is dynamically controllable. And so these are just vocab words. I'm not explaining anything to you yet. So so we were trying to find a negative cycle, or we were trying to find something that approximated a negative cycle, and we knew sort of immediately a negative cycle wouldn't work. And so instead, the thing that we're looking for is something called a semi-reducible negative cycle. So a semi-reducible negative cycle is a cycle. Its weight is negative. And the big thing about it is that if we take this cycle of edges and we iteratively apply those rules that we saw previously on this page, just these 5 rules, this is not all set of possible rules. But if we apply these 5 rules sort of ad nauseum to this cycle, and we find that after applying all these rules, we have no lowercase labeled edges, this suffices as a proof that the STNU is not dynamically controllable. And this is a necessary and sufficient condition. If we cannot find a semi-reducible negative cycle, then we know that the STNU is dynamically controllable. So jumping back to your earlier question about can we have both lowercase and uppercase labels of the same type, the answer is yes. If you find a negative cycle that has a lowercase and uppercase label of the same type, it is possible that suffices as a proof that the STNU is inconsistent, but it has to be the case that lowercase edge is removed through the application of one of these rules. So that was sort of the nuance associated with it. But the really nice thing about this is, this whole notion of a semi-reducible negative cycle being there if and only if the STNU is dynamically controllable is the exact same idea that we had when we were talking about the STN. And so now, the big question is, how hard is it going to be for us to actually find the semi-reducible negative cycle? And the answer is, it's not super hard, but it takes you a little bit of time to sort of wrap your head around what's happening. So I'll try to walk through it, and then I promise I will give you an example, and when we walk through the example, it'll make a little bit more sense. So we want to find semi-reducible negative cycles. And how do you find a semi-reducible negative cycle? Well, the first thing that we want to do is sort of walk semi-reducible paths, right? If we think back to STNs, we said, hey, if we walk this path, this nice, we get these sort of nice derived constraints. We want to do the exact same thing, but now we're walking semi-reducible paths. But the big problem with walking a semi-reducible path is that you have to actually keep track of a lot of state. And the reason for that, and one of sort of the big reasons for that, is if you sort of walk forward in one of these labeled distance graphs, you have to sort of be prepared to reduce away your lowercase edges at any time. And in fact, you might in fact be walking a path and stacking many lowercase edges, none of which you've reduced. And then at the end, you find a big negative edge, and you propagate that negative edge backwards in order to reduce everything away. And so it turns out it's kind of hard to sort of like keep track of all this and making sure that you're not doubling back on yourself or ignoring something. But Dijkstra's algorithm actually, we can modify it in kind of a nice way that allows us to reason about it pretty well. And Dijkstra's algorithm will get us pretty far. But one of the big problems is Dijkstra's algorithm only works if you have non-negative edges. And as we discussed earlier, and with that example over there, we have negative edges potentially in our graph, in our labeled distance graph that we have to deal with. Our STN had negative edges. So Dijkstra's, sort of one caveat: if we can provide a guarantee to Dijkstra's algorithm that the only negative edges it will see are the ones that are immediately connected to the starting node, then Dijkstra's algorithm still works fine. So this is sort of one caveat that we can use to maybe try and sneak Dijkstra's algorithm in a little bit if we sort of use it multiple times. And then really quickly about the algorithm that I will discuss, this algorithm is going to search for semi-reducible paths backwards in the graph. Don't worry too much about it. It turns out just that if we sort of walk backwards, then it becomes much easier for us to eliminate these lowercase edges as we go, sort of in an appropriate fashion. But don't worry too much about this. If you have more questions about exactly why, you can come and ask me later. But so now this is sort of the crux of the algorithm. So we take Dijkstra's and we want to modify it in a way to guarantee that we can find semi-reducible negative cycles. And so the way that we start is we search for semi-reducible paths. And we're going to start from, our end goal is we want to find a semi-reducible negative cycle. So we're going to start by considering all nodes that have an attached negative edge. And so what we're going to do is we're going to just walk. And if we can sort of add new edges onto our walk such that the semi-reducibility of the whole path is preserved, we're going to continue our walk. And so one of two things happen. Either this path terminates or it doesn't. So if it terminates, we're kind of done. But one sort of problem that we might run into, again, the one that we discussed earlier, is this graph has a lot of negative edges in it. So what happens if we run into another negative edge? Well, our approach in the moment is we're just going to stop and we're going to just recursively call our version of Dijkstra's algorithm again and just keep going forward. And the idea here is we want to maintain semi-reducible paths as far as we go, and sort of taking this recursive approach will allow us to at least have partial semi-reducible paths that we build up. But the big question is, how does any one of these recursive calls return? So one, if the path ends, great. But like in all of the graphs that I've shown, they're basically all full of cycles. Everything is connected to everything else. It's very unlikely that any of these paths will actually terminate. And so the way in which we actually say that our walk is going to terminate is if our semi-reducible walk eventually becomes positive, then we stop considering that walk any further. And so the idea here is we walk through our graph. So we start from some node. We start from a negative edge associated with it. So we start with a negative path weight. And if that path weight eventually becomes positive, we have a semi-reducible path that in its totality becomes positive. And so what we're going to do is we're going to actually take that entire path. It is semi-reducible. And so we're going to add a single edge back into our graph that represents sort of that full walk. And so the advantage of this is that if we now think about it, if we have a recursive call that returns, that means that every walk from that negative edge that we saw is either going to terminate or become positive again. Yes, question? Oh, no, great. It's either going to terminate or become positive. So if the recursive call successfully returns, then we can actually safely ignore that negative edge and continue with our Dijkstra's algorithm. Because, again, we're searching for a semi-reducible negative cycle. So if that negative edge leads to a path that terminates, great, we don't care to take it. If that negative edge eventually becomes positive, then we're going to just take the big positive edge shortcut to jump forward. And so if eventually everything terminates, then we're happy. But of course, the question is what happens if we infinitely recurse? If we infinitely recurse, then we know we have a semi-reducible negative cycle. Because at every step of the recursion, we have this guarantee that we're maintaining a semi-reducible negative path that we have walked, and then we recurse, and another semi-reducible negative path. And eventually we return back to the beginning, and if we string together a bunch of semi-reducible negative paths, we have a semi-reducible negative cycle. Certainly a lot. I don't expect everyone to have followed along, especially because we're like 70 minutes into the talk right now. So here's an example. Hopefully the example makes a little bit more sense, at least with respect to what I'm trying to explain. And so this, it's worth noting that this is not actually an STNU. This is just a labeled distance graph that we're discussing. But we have this nice sort of analogy between every STNU we can turn into a labeled distance graph. And so all we just care about is searching for a semi-reducible negative cycle in any labeled graph. So the way that we start our algorithm is we start by looking for negative edges and seeing what nodes are connected to them. And so here I see that A is connected to this negative 10 edge. Again, we're going backwards. Don't worry about it. And so I'm going to start my Dijkstra's algorithm from here. And so I see that the shortest path from A to B is exactly negative 10. I continue my walk, and I see the shortest path to C is negative 9. But now I have a negative edge. I have, in fact, this negative labeled edge. And so what I'm going to do is I'm just going to recurse. I'm going to pretend I never started at A, and I'm going to start at C instead. And so now from C, I know that the shortest path from C to D is weight negative 1 with sort of this condition attached to it. Shortest path from C to E is 0 with this conditional attached to it. For reasons that I didn't get into, it turns out that you can actually drop this uppercase conditional when it becomes non-negative. Don't worry about that at this moment, just sort of trust me on that. But the thing to sort of take into mind is that our walk has now become non-negative. And because our walk is non-negative, we're not going to sort of continue this walk, and we're just going to add the edge back to the graph immediately. So we now add this new 0 edge back to the graph. And there's nothing else on our Dijkstra's queue, so we're just going to continue. Or we're going to return. excuse me. So now we've returned, and we're back at sort of our shortest paths starting at A. And because our recursive call successfully executed, we know that it's safe for us to just ignore that f-1 edge entirely and just consider all non-negative edges that sort of continue from that point. And so I can actually take now this edge to E with -9, and we'll see that the next edge that I have coming up is this lowercase labeled edge with an f. And I can actually take this edge and consume this edge with that lowercase reduction that we talked about previously. And so now, sort of the really nice thing here is, in our example, we had two edges that were sort of close to each other that had the same label. One was uppercase, one was lowercase. But by virtue of this reduction, we're actually able to ignore those labels altogether, and we're basically just searching for a negative cycle at this point. And so what we're eventually going to do is we're going to continue our walk, and we're going to get back to A, which is our starting point, with a weight of -3. And so we're going to see that there is a semi-reducible negative cycle present. All right, great. So we have this algorithm. I told you that it ran in polynomial time. I took a long time to explain it. Now I'm going to tell you why it actually runs in polynomial time. So, so the big thing to realize is that we need to actually call our version of Dijkstra's algorithm for every node that has a negative edge connected to it, just in case that one starting negative edge is the one that sort of completes the entire negative cycle. So in the worst case, we actually have O of n total calls to our modified version of Dijkstra's algorithm. And Dijkstra's algorithm, we know, runs in O of m plus n log n time, where m is the number of edges and n is the number of nodes. But the big problem is the fact that we're actually sort of modifying this graph as we go. We're actually adding edges to the graph as we continue forward. And so what we see is that instead of it, in the worst case, there will actually be O of n squared edges in the graph as we sort of march through it. And so instead of taking O of m plus n log n time, each call to Dijkstra in the worst case will take O of n squared plus n log n time, which is just O of n squared. And so the total runtime of our algorithm is going to be O of n cubed. And so this result is roughly 5 years old at this point. It sort of stood for quite a while. And it's actually pretty good. And if you code this up and you try and run it, it runs remarkably efficiently. It actually runs much better in practice than sort of the O of n cubed time suggests. And a big part of the reason for that is that you don't actually hit these absolute worst case numbers that we've talked about. And so this algorithm, while it was sort of a little complex, a little meaty, at the end of the day, it's really just Dijkstra's with a little bit of flair to it. And so if jumping back, if you have sort of your planning algorithm, you generate a candidate, and you now have actions that have some sort of temporal uncertainty associated with them, we have a remarkably efficient algorithm for actually checking whether or not you can construct a valid schedule, whether it's actually dynamically controllable. And you can do so in O of n cubed time. And of course, the next question that you want to ask is, how can we actually, can we sort of fold this in more closely to our algorithm? Can we sort of incrementally adjust sort of our incumbent partial plans and sort of use this information to guarantee dynamic controllability as we go forward? And there are quite a few works that have sort of addressed this problem and sort of examined it: fast IDC, efficient IDC, and EIDC2. EIDC2 is sort of the incumbent as the best sort of incremental dynamic controllability checking algorithm. It actually runs in O of n cubed time as well, and actually sort of the approach that it takes is in a lot of ways extremely similar to the approach that we just discussed. They have sort of the leeway to sort of be a little bit smarter, and they don't have to consider absolutely everything whenever you sort of add a new constraint, but sort of the worst case runtime is still O of n cubed. But when we sort of take all of this together, we now can actually do quite a lot. We can take our planning problems, and if we have temporal uncertainty in them, we know how to model that as a sort of temporal scheduling problem with temporal uncertainty in and of itself. We know how to sort of check candidate plans for temporal controllability in one shot. That was sort of the big, complex, gnarly algorithm we talked about earlier. And then we also know how to maintain a data structure for incremental consistency checking. And in our case, instead of it being a distance graph, it's going to be some flavor of this labeled distance graph is what we're actually going to use at the end of the day. And sort of, in terms of what I was hoping to present today, this sort of wraps up sort of section 1. This is sort of a deep dive of a lot of sort of the fundamental aspects and fundamental things that you're going to see when you think about adding temporal reasoning to your existing planning subsystems. When we come back after the break, the first question that we're going to ask is, in the world of STNUs, can we do better? And can we be smart? Is there some sort of easy thing that we can do in order to be smart and actually be more efficient about the way in which we evaluate dynamic controllability? And we'll go into some additional types of temporal networks, considering probabilistic uncertainty, and also we'll finally return to the question of, if you're sort of in a multi-agent world, how can you use temporal modeling, temporal reasoning to your advantage? That's it. Any questions before we go? Yeah.
If we have one event with uncertainty, couldn't we just replace this by two events, one at the earliest possible occurrence, one at the last possible occurrence, with a temporal relation, which would then reduce the whole problem to a simple temporal network without uncertainty?
Yeah, so that's sort of a great intuition. So if we jump back to the example with like the movie theater, et cetera, we absolutely could do this. And in fact, so when you consider strong controllability, there's a very natural way in which you take more or less exactly that same approach to evaluate strong controllability, and it reduces to the same type of LP/STN that we talked about previously. So if you just want to pre-compute a schedule and basically say, for all the events that are within my control, can I come up with a guarantee? That approach works perfectly. That is the approach to take. If you want to have sort of one of this more online sort of policy-making things, then that approach doesn't quite work, because sort of when you take that approach, the intuition there is you're saying, so I have like almost an event B and an event B prime, so B might be at 20 and B prime might be at 40, and I want to make sure that this relation between B and C is still 30 to 45, and this relationship between B prime and C is between 30 and 45. That would be the approach that you would take if you were to sort of split it into two, and so that sort of binds you to sort of requiring that you satisfy both the lower bound and the upper bound simultaneously, whereas in this example what we showed is you can't satisfy both the lower bound and the upper bound simultaneously, but you can adapt on the fly. Any other questions? Yes?
Maybe a more practical question. Do you know of any library which would provide those algorithms that I don't have to sit and
It's a fantastic question. For the STN ones, certainly. Those are off the shelf, like Johnson's algorithm, Bellman-Ford. But
specific STN packages.
STNU or CSTN?
I do not know of any off the top of my head, but that doesn't mean they don't exist. I don't know if you know of any. Okay. At the current moment, no.
well, Google was telling me the same when I was like trying to search for some C++ or Python library, even just for STNs.
Yeah.
I found like one GitHub repository, but still not that very successful.
Good point.
Yeah.
I see one in Italy.
I would believe that, yes. Maybe some of Peng's stuff might be.
So we should consider that.
Yes.
Develop one.
Yes, definitely. It's a good question. Any other questions? In that case, we will resume in 40-ish minutes for the second part. Thank you for your attention.